My topic is non-commutative analogue of Nazarov-Podkorytov lemma. It is joint work with two lemma. There is, I said, about keep some formulation and the introduction, and the second part of the main results. This let us introduce the following Ball's inequality. For equal to t, it turns into an identity. A new interesting problem, Ball's inequality, was given in 2000 by Nazarov and Podkorytov. A reformulation of Ball's inequality let if x equals to exponential power minus p x is square of x over 2, and the g x equals to sinus x over px, and for all positive x. Then by the Euler-Poisson formula, the Ball's inequality can be rewritten as this form. And for every f greater than 2, with equality when f equal to 2. Thus, we need to compare alpha norms of f and g. This means for phi greater than 2. And give some definitions. Let omega n be a measurable space given a measurable function f. It is distribution function of distribution function is defined by this form. This is measurable of x, and for such that absolute value of fx greater than s for all non-negative s. Suppose there exists a positive c such that f and g satisfying the following inequality for all non-negative s. Then, if the norm of phi norm denotes the norm of LP omega, and g norm of p norm of g less or equals to c power 1 over p multiplication per norm of the f for all p greater or equals to 1. But it cannot be proved by this method, by this standard method. Doesn't work. There is, because indeed, since this for this equality, and it follows that this means this equality holds for this, and therefore there exists positive c0 such that the function changes its sign at s0. It means this distribution function of f and the distribution function of t, here, like that, change 1 s0 at that sign. Therefore, there exists s0 at its sign at s0, and consequently, this 1.4 cannot be held with c equals to 1 for all s. For cannot be solved this inequality because there is 1.4 set. There is TSC less than the same. This distribution function of f, but this means not hold that is changed at 0 sign. And let this Nazarov-Podkorytov lemma set. Let f and the g be two measurable functions such that their x is positive C0, for which these inequality distribution functions interlaced. F and the g's distribution functions are interlaced. And the search more. Suppose there exists P0 greater or equals to 1 with this inequality. And then the Nazarov-Podkorytov lemma asserts that for all P greater than P0, such that this function in L1. And we have the following inequality. It turns out that the function f and g defined in 1.2 fx exponenta there is and the gx like that fx minus px square 2 and gx equal to sinus px over px. Yes. It's 1.2. And satisfying the interlaced formula for some S0. Consequently, since 1.6 is valued for 0 equals to 2. By the above result, we get 1.3 and hence 1.1. It is both inequality. This 4 and 1.6 is and interlace 1.5 and there is 1.2 this and we from 1.3 we can take this both inequality 1.1. And we give some definitions of non-commutative version. Let H be a complex Hilbert space and PH be an algebra of all linear bounded operators on H. Let us denote by M subset of PH a semi-finite von Neumann algebra equipped with a faithful normal semi-finite trace tau. The pair M tau is called non-commutative measure space. A closed and densely defined operator x on H is said to be applied with M if this x and u commutative u star x u equals to x for each unitary operator u in the commutant of M. The operator x is set tau measurable if x is applied with M and for every epsilon there exists the projection P in M such that PH subset of domain X and this trace of 1 minus P less and then epsilon. Then the set of all tau measurable operators we will denote by this L0M. And let XP tau measurable operators, and the distribution function of X is defined by this trace of spectral projection of X. It is clear that the function, the X from 0 infinity to 0 infinity is non-increasing, and the normality of the trace implies that distribution function of X is right continuous. Let X, Y be tau measurable operators, and such that there X is positive C0 for which is interlaced for X, a distribution function of X, Y. For X, tau measurable operators X, the generalized singular valued function of X is defined by this formula. And the function T is from T to mu to X is decreasing and right continuous inverse of the distribution function of X. Applying the Beijing's lemma for the function fx equals to x, we obtain the following equality. For Lorentz, the non-commutative Lorentz Q space is equal to the quasi-norm for like C defined. And this we combine these results for Han and Beijing's result. If Q equals to P, we can take LP norm. This is definitions of the non-commutative Orlish space, and this let P be a Orlish function on 0 infinity. It is Orlish function means it is continuous increasing and convex function. This definition satisfying P0 equals to 0 and limit of the phi t equals to t infinity. For any x tau measurable operators X, phi by means of functional calculus applied to the spectral decomposition of X, we have this following equality, and we combine this literature and these results. See for more information on Orlish functions and Orlish space for Mali Granda book we combined. And for an Orlish function P, the non-commutative Orlish space LPM is defined as the space of all measurable operators with respect to m tau, such that this trace of phi less than infinity is finite. For some positive C, the space LPM equipped with the norm like that in prime of C for trace, this P trace greater than less than 1, and is the Banach space if phi t equal to Tp with this P, then Orlish space equals to LP spaces. These are our main results. Next. Let X and Y are tau measurable operators will be chosen to satisfying condition 1.8. It is interlaced distribution functions are interlaced x and y. Assume that there exists p0 greater or less than greater or equals to 1 with this trace non-negative, and at least one of this absolute value x power p and absolute value of y power p has finite trace provided with p greater than p0, and this operator in L1 space. Then this trace non-negative, in particular, returns this p comparison these LP norms for these LP norms, and this following results for Lorentz space. This let P0, Q0, and the P, there is comma, mistakes, there is comma. P0, Q0, P and Q are positive, and let one of the following conditions satisfied. Assume that x and y are tau-measurable operators, and we will choose the satisfying condition interlaced for these distribution functions x and y are interlaced. If this inequality holds, and if this function in L1, then this inequality holds for all PQ, like that. As a consequence, if at least one of the operators x and y in LPQM, then this will Lorentz norms with comparison x and y Lorentz norm, and this is for Orlish space for Nazarov-Podkorytov, and let xy in L0M will be chosen satisfying the condition interlaced. Assume that there exists P0 greater or equals to 1 with this inequality holds, and let phi be Orlish functions, and let the following condition is satisfied, then this trace for trace is inequality holds. In particular, there is also this norm of Orlish norm of the x and y. Thank you for